Section 3.3 is on page 186, talks about concavity and the second derivative test. So just like we did maximum and minimum, concavity is kind of the same idea, universe of increasing, decreasing. A curve that is concave upwards lies above its tangent line. A curve that's concave downwards lies below the tangent line. Well, we're going to get a bit more than that from this. If I look at a curve, this is a curve. Concaving up is really when it's looking like a parabola opening upwards. Concaving down is when it looks like a parabola opening downwards. You imagine a smooth parabola. If it's opening down, we say the graph is concaving down. If it opens up, we say the graph is concaving up. And checking where the curve lies above or below is not really what we do, because we're not going to look at the graphs. We're going to use algebraic work. But this is what we notice. We notice that if a curve is concaving up, we notice that the slope is positive. The slope of the tangent is positive. And if a curve is concaving down, we notice the slope is negative. And we know the slope is a derivative. So, if the derivative is increasing, we say the curve is concaving up. And if the derivative is negative, we say the curve is concaving down. Pretty much identical to you saying, let's take a second derivative test, and kind of the same idea. If the second derivative is positive, we say the function itself is concaving up. And if the second derivative is negative, to the right of A, we say the curve is concaving down. And if we go from concaving up to concaving down and down to up, we call that inflection point that's coming up. So the test for concavity is pretty much what I just said. If the second derivative is positive, the curve is concaving up. If the second derivative is negative, the curve is concaving down. And here we're trying to look at, make sure we see this concavity business. State the sign of f prime and f double prime on the interval. You notice that this curve is, if I continue this trend, it's concaving down. If it's concaving down, we say that f prime is increasing and f double prime is positive. And if you look at this graph, if you continue this curve as a smooth curve, you'll notice that it's kind of like a parabola opening up, so we say the derivative is decreasing. F prime is decreasing. And f double prime is negative. Okay, I said those backwards, didn't I? This is negative, and this is positive. My mistake. So we're gonna tackle that in a couple of problems. It says, determine the open interval where the function is concaving up or concaving down. So I write this as negative 5x to the 1/2. So I need two derivatives. The first derivative will be negative 5/2 x to the negative 1/2. And if I take a second derivative, that will be positive 5 over 4x to the negative 3/2. Now, I need to figure out, this is 5 over 4, the square root of x cubed. So, if I try and figure out where is the second derivative 0 and where does the second derivative not exist, the same idea as the first derivative test, this is the second derivative test. Well, there's no way a fraction could equal 0 here because the top can never equal 0. But where is this derivative not exist, that's when the denominator equals 0, that's when x equals 0. So I only have one point to worry about. If I pick 0 and I take the second derivative, and my conclusion is about f, and the same deal as before, if I pick a point to the left of 0, well, that's not possible because it's not in the domain. Domain x has to be bigger than or equal to 0, right? So I only have to test this point. If I take 1, if I put 1 in there, the top is always positive, denominator is positive. If the second derivative is positive, the graph is concaving up, and we state that. We say f is concaving up, CU for concaving up, CD for concaving down, from 0 to infinity. F is concaving up from 0 to infinity, and that's pretty much it. If I get to number 10 and do the same thing, well, you'll notice here that algebra is the tricky part. Minus the top times the root of the bottom all over the bottom squared. That's busy work, and I need to clean that up. That is 8x minus 2x cubed, that becomes a positive, plus 2x cubed plus 8x all over 4 minus x squared squared. I notice those cancel out. The first derivative is 16x divided by 4 minus x squared. Well, I need the second derivative. So if I take the second derivative, that would be the root of the top times the bottom minus the top times the root of the bottom. Bring the power down. Subtract 1 from the power, times the root of the inside, all over the denominator squared. The second derivative would be, and here it will be easier to factor the 16 and the 4 minus x squared. So it's easier to take 16 out of both of those and that to the 1 power. What that leaves me with, out of the first, that will leave me with, you know what, there's not enough space, let me fix this. So I'm going to continue this here. Again, all what I did was I moved some of those down. 16 into 4 minus x squared times. Out of this term, I'll have 4 minus x squared left. And negative times a negative is a positive. I took the 16 and this. I'm left with 2x times 2, which is 4x, times x, and it's positive. So 2 times x times 2x, that is 4x squared, all over the denominator to the fourth. And I notice this cancels one of those. And now I'm going to continue the rest up there. Now I should have room. And that's going to be 16 times 4 plus 3x squared divided by 4 minus x squared cubed. And I need to figure out where the second derivative equals 0, where the second derivative does not exist. So the derivative does not equal 0 when 4 plus 3x squared equals 0. That's not possible. And the derivative does not exist when 4 minus x squared cubed equals 0. That's 2 minus x into 2 plus x equals 0. So I have x equal 2 and negative 2. So I need to test negative 2 and positive 2. And I notice the top of this is always positive. The denominator, if I pick a point to the left of negative 2, let's say negative 3. Four minus 9 is negative cubed, that's a negative. If the second derivative is negative, the function is concaving down. I pick 0. If I put a 0 there, 4 minus 0 is 4 cubed, that's a positive, the graph is concaving up. And if I take 3, 4 minus 9 is negative again, the graph is concaving down. So we say f is concaving up from negative infinity to negative 2, union with 2 to infinity, and we say f is concaving down from negative 2 to 2. Now what's coming next? Do you see how this changes from concaving down to concaving up? We call that an inflection point. And do we see that here it was concaving up, now it's concaving down? We call that an inflection point as well. Kind of like a minimum maximum thing. So the graph must change concavity for it to count as an inflection point, and here it is. They're stating that in a definition. They say if the graph of a continuous function has a tangent line at a point and its concavity changes from up to down or backwards, then that point is an inflection point. So if I think of parabolas, if I graph a parabola, this should look like a parabola. Well, that's concaving up, and do you notice this is concaving down? So this, again, I'm thinking of parabolas. The point where you think the graph switched from concaving up to start concaving down is the point of inflection, or simply inflection point. If I look at this graph was concaving down, so if I continue that like a parabola, it looks like this. This graph is concaving up. So again, where do you think that point is? That's the point of inflection. It could come in many forms. Again, that's like a parabola. And if I continue this like a parabola, this graph is concaving up, now it's concaving down, and that's the point of inflection right there. So the next step is to pretty much do the same thing. Discuss the concavity of the graph and find the inflection point. Did I give you a page number on this? Yeah, 193. If I take the first derivative, that is negative 12x squared minus 16x, and if I take the second derivative, negative 24x minus 16 equal to 0, that's when x equals 16 over negative 24. That is divided by 8, that's a 2 divided by 8, that's a 3. So I have one point to test. It's a possible inflection point, but we're not sure. There's the second derivative, there's f. If I pick a point to the left of negative 2/3, let's say negative 3. Negative 3 right there, that will make that 40, or negative 2. 48 minus 16 is positive. And if I pick a point to the left of negative 2/3, let's say 1. If I put a 0. A 0. If I put a 0 there, that would be negative. So concaving up, concaving down. Then we say, and here they're saying, discuss the concavity. F is concaving up from negative infinity to negative 2/3, and F is concaving down from negative 2/3 to infinity. We do have an inflection point at x equal negative 2/3. We could plug that in and figure out what the y is and put it as a pair when we graph. For now, it's enough for you to figure out whether the point is a point of inflection or not. 18 is another example. If I take the first derivative, that is 8x to the cubed minus 24x squared plus 24x plus 12. And if I take another derivative, I'll get 24x squared minus 48x plus 24. I want to know where does that equal 0, but this is defined everywhere. If there's no point in testing where is it undefined. You factor a 24 out of that, you'll have x squared minus 2x plus 1. So this is 24 into x minus 1 squared equals 0. That means x must be 1. And this is a possible inflection point. Let's test and make sure. There is the 1. There is, I'm still stuck on f. there is G double prime, and there's G. A point to the left of 1, let's say 0. If I put a 0 right there, that cancels out. I'm left with a positive 24. If I put, or right there actually is easier. If I put a 2 in there, 2 squared is 2 minus 1 is 1 squared. That's a positive. So this graph is concaving up, concaving up. We say F is concaving up from negative infinity to 1, union with 1 to infinity. So since it was concaving up, then concaving up, that's not an inflection point. You must change direction from concaving up to concaving down, or vice versa. And this is the main use of an inflection point in your field. If you think of this as a parabola, think of this as a parabola coming down. That is a point of inflection. It is called in application the point of diminishing return. And what that is, in economics, the notation of concavity is related to the concept of diminishing return. X, measure the input in dollars. Y, measure the output in dollars. In figure 330, that's this figure right here, notice that the graph of this function is concaving up from A to C, and it's concaving down from C to B. On the interval from A to C, each additional dollar of input returns more. You'll notice this is increasing. This point, it's still positive, but it's no longer returning as much. By contrast, on the interval from C to B, each additional input is giving less than the previous input dollars. The point C, this point right here, C, F of C, is called the point of diminishing return. An increased investment beyond this point is usually considered a poor use of capital. You want to get to that point and then stop it. No need to invest anymore. Look for something else. And here's a problem. It says in exercise 6162, find the point of diminishing return of the revenue where revenue in thousands of dollars, where X is the advertising cost in thousands of dollars. Well, we'll take our prime, bring the power down, and that will become 4/3 x squared plus 8x. Take another derivative, that is negative 8/3 x plus 8, set that equal to 0. That means negative 8x plus 24 equals 0. I cleared the fractions. Negative 8x equal negative 24, x would be 3. And here, since this is in thousands of dollars, whoever is doing this wants to invest at most $5,000. So if you do the testing, take 3, there's R double prime, and there's revenue. A point to the left of 3, let's say 1. You put a 1 right there, or there, it doesn't matter. Negative 8/3 plus 8 is positive. You put a point to the right, let's say 4. If I put a 4, easier to do here. A 4 in here, that's 4. Negative 32 plus 24 is negative. This graph was concaving up, now it's concaving down. So the point of diminishing return is 3, and if I take negative 4, actually we have a calculator, right? Let's just use that. If I take negative 4 divided by 3, parentheses, 3 cubed, which is 27, plus 4 times 3 squared, which is 9, plus 12, I'll get a 12. So that's the point of diminishing return. I could go to the previous problem if I needed and plug in negative 2/3. I could take a negative 4 times 2/3 raised to the third power minus 8 times 2, a negative 2/3, but you're squaring it, so it doesn't matter. Oops. 2/3 squared plus 32, and that will give me a fraction of 732 over 27. 736 over 27. Okay, well, with a calculator, that's not that bad. And one more to go. If I wanted to do inventory cost, the cost in dollars of ordering and storing X units is given by this equation. What order size will produce the minimum cost? You want to minimize your cost always and maximize your revenue or profit. Well, if that's the cost function, that's where the derivative equals 0 undefined. That's a 2. Now I'm going to write C before I go here. I'm going to write C as 2x plus, it's easier to write this as 300,000 x to the negative 1. This way you don't have to avoid using quotient rule. Here you bring the power down, subtract 1 from the power, and that makes this equal 2 minus 300,000 over x squared. And you want to know, where does that equal 0, or is it undefined? Well, I could even, you really could get around this, but it's easier to see it this way. Let me just move this down just a bit. Okay, and move this down just a bit. There we go. So, now if I was to say, where does C prime equal 0? Where does C prime not exist? Well, it doesn't exist when x equals 0. That's very easy. Do not order or store any units, and you don't have to pay a penny. But if I go for this, right, and that's not an option, by the way, but it's okay because it's not in the domain. So it doesn't make sense for you to figure out where to minimize cost and you say, you know what, don't buy anything. That's always the case. Where does 2 into x squared minus 150,000 equal to 0? That's when x squared equal 150,000. And if you square both sides, I need to take the square root of 150,000, and that is 387 units. So it turns out the minimum cost occurs when x is 387 units. If you order 387 units based on this cost function, you will be minimizing your cost. And the homework is right there, section 3.3, page 193. And that concludes this section.